Let's now learn how to work with the expectation of variance in situations where you have more than two random variables. Good news, there's nothing else you need to know. We can generalize everything that I mentioned before on our previous lesson or previous video for situations involving two or more random variables. So let's say that you have x1, x2, x3, xn as n independent random variables. T, a new random variable which is given by ax1 plus or minus bx2 plus or minus cx3. You can think of any variation possible. The expectation of t is going to be given by the expectation of the expression itself, which you can break down to a times the expectation of x1 plus or minus, depending on which one you have, b times the expectation of x2 plus or minus c times the expectation of x3, etc. All right? Applying what you learned last lesson, the variance of t is going to be slightly different. So for each one is going to be a square, the variance of x1. It's always going to be plus, even if this is minus, you keep adding. B square, the variance of x2, plus c square, the variance of x3, etc. So it's basically what we learned last lesson, but now all of this, but now applied to many more random variables, an arbitrary large number of random variables. More things. If the distribution of x1, x2, x3, etc. can be modeled as a normal distribution, so will the distribution of the sum t, in which t is given by ax1 plus or minus bx2 plus or minus cx3, etc. So if you can model if you can model this by a normal distribution, so this sum can also be modeled by a normal distribution, and the parameters are going to be obviously the expectation of t and the variance of t. So once you get that, you have all the information required to calculate probabilities using the normal distribution. Note one thing. In some situations, you will have the expectation of x1 and the expectation of x2 being the same, okay? And the variance of x1 and variance of x2 being the same as well. I want you to pay attention to this difference, okay? The expectation of 2 times x1 and the expectation of x1 and x2. You use this only when you have 2 times the measurement of x1. And you use this when you have 2 different measurements of x1 and x2, albeit the fact that they are the same. That is not very relevant when you're calculating the expectation. As you see, the result is going to be the same, okay? You can generalize this for x1 plus x2 plus x3 plus, in which case for 3 this will be 3, for 4 it will be 4, etc. You get the point. They will be the same nonetheless, but when you are calculating the variance, they are not going to be the same. So you have to pay attention to what situation you are dealing with. Most of the cases, in most of the exercises that you are going to solve, is going to be this one, okay? I'm giving you an example from real life. Let's say that you are measuring x1, or x represents the length of a tile, a square tile. You have 2 ways of making this measurement. Either you take the measurement of x1, the length, for example, and you assume the height to be the same because you trust the fact that it is a tile, or you take the measurement of x1 and x2. They are supposed to be the same, but you take 2 measurements nonetheless. So if you take 1 measurement only and trust the fact that this one is going to be the same as this, you would use that case. In the second case, you would use this case. Again, most of the questions that you are going to find, you have to look at this only.